Hello and welcome to part 2 of our discussion of exponential functions. We're going to look now at a very special base for an exponential function. In the last video, we saw that if I have b to the x is how I calculate y, we say we have an exponential function, and b had to be greater than 0 and not equal to 1. Well, e is a number that fits this constraint of being greater than 0 and not equal to 1. Now, you probably haven't thought of e as a number in a long time, or if at all. We use it mostly as a letter, but notice it's a little bit of an italics E. If you look at your calculator, there is at least one button that has an E on it. And the TI-84 calculator, there is a button that has just the E, and it's below. So you have the clear button, and then you have the button that has this and has the pi on top of it. The next button down, the division key, has an E on top of it. And if you press that, if you do second and then press that division key, you will get this number show up on your screen. The other and more useful place it shows up on the TI calculator is over on the left-hand side, 3 up from the bottom. You have a button that says LN, and we're going to talk about that in the next unit. And above it, there's an E to the X. If you press that, you get E. You either get E and the cursor goes up here. If you have a new operating system, or on mine it goes E, and then I put a number, so I can do like E squared or E cubed. So this E is a number, and it's called the natural exponential base. It shows up all the time in nature, and it's also a base that if you want to compare exponential functions, writing them both as base E functions becomes a convenient thing to do. So let's practice this on the calculator. Here's what you do on a scientific calculator like a TI-30 or on some of the Casios that you have. And here's what you do on the graphing calculator. Make sure you can evaluate E to E cubed. And I will tell you what you're supposed to get right now. So I will press second E to the X, put a 3, and you're supposed to get, I don't know why I didn't have this on the slide, you're supposed to get 20.85536.9. That's enough. That's more than enough. Usually 4 or 5, like you probably would round that to a 4 and cut off there. But so that's what you should get. Make sure you can do that on your calculator. Now, again, I can do things to my basic function, e to the x, is our basic exponential function with base e. E is a number, it's about 2.718. But it's one of those numbers like pi that goes on forever. But your calculator has it stored to enough digits, you don't have to worry about that. But just remember, it's a number between 2 and 3. E is between 2 and 3. It's a little closer to 3. Later on in mathematics, that will become a useful kind of thing to remember. But here, I cannot multiply 2 times e first. I have to do e to the 0.3x. Now, I'd like you all to try evaluating this on your calculator. And tell me what you get. Make sure you can do this. I would like you to find big F here of 2. So I want to make sure you can do this on your calculator. And I'm doing that right now. And you should get 3.644. If you let x equal 2, it becomes e to the 0.6 times 2. And you should get 3.44 in your calculator. Sorry, 3.644. 3.644. So make sure you can do that. If you're having trouble, email me. Let me know what kind of a calculator you're using. That would be helpful. All right. Now, E has some applications in business, too. It's not just in science and engineering. It comes up in business as the base of the continuously compounded interest formula. And a lot of times exponential growth is modeled using E to keep a consistent base. But compound interest and simple interest, there's a difference. The power of compound interest is very important to understand, especially if you're young, because money invested now makes money, and then that money makes more money. That's the principle of compound interest. Simple interest is calculated once and based only on the original investment and either you take that out as cash or it doesn't stay in the account and continue to gain interest. Simple interest is easier to calculate, so we'll start with that. Anytime you make an investment, we call the amount you invest the principal. And so the amount you have after simple interest is the principal plus the interest. So the interest would be the principal times the rate of interest. And this is just assuming it's in there for one term or 1 year. So R is the rate as a decimal. 5% would be 0.05, 2% would be 0.02, 15% would be 0.15. You don't see that much when you're gaining interest. Compound interest gets computed on your original investment in any accumulated interest. So if you were going to compound this interest, this P plus PR becomes your new principal for the next term when you make a calculation. So this is about how this goes. If you were doing compound interest from the simple interest formula, and we're assuming you're compounding yearly, at the end of the first year, you get P times 1 plus R. At the end of the second year, you get P times 1 plus R squared. At the end of the third year, you get P times 1 plus R cubed. At the end of the fourth year, you get P times 1 plus R to the fourth. Let's take a look at where that second one comes from. All right, let's look at that algebra right now and see how that works. So, when I go into the second year, at the beginning of year 2, my new principal is what I ended up with at the end of year 1. So, at the end of year 2, I will have my new principal plus that new principal times the interest rate again for interest. And what I can see, if I were good at factoring, is this is actually a greatest common factor, and I get P, if I remove that, P times 1 plus R, it leaves me a 1 here, and it leaves me an R here. I know it's a little hard to see, and that gives me P times 1 plus R squared. And it'll work this way every time going down the list. So so if every year, if you were compounding yearly, this is what you would get. And you can see this is growing. This exponent is getting bigger every time. So you don't have to compound just yearly. You can compound quarterly, monthly, daily. Sometimes if you take out a banking instrument, if you invest in a banking instrument called a certificate of deposit, they say whether you compound quarterly, monthly, daily, etc. Now interest rates are pretty low now, so nobody pays as much attention to it, but when I was younger and interest rates were very high in the early 80s, it made a big difference whether you were investing in a compounded daily or a compounded monthly or compounded quarterly kind of certificate of deposit. A lot of people made a lot of money off of those because interest rates were outrageously high. So here is the formula. Now the trick to this formula is knowing what each item represents. You won't have to memorize this. This will be given to you. You're encouraged to look at it while you're doing the homework, but P is the amount you invested. P is the original investment. This 1 is just part of the formula. R is the rate as a decimal. So if your rate is 5%, and we'll assume that's annually if they don't say it's annual, that means you're going to use R equals 0.05. You have to take that 5% and write it as 5 over 100 to use it in the formula. You never use the straight percent. You use the decimal equivalent. N is the number of times per year it's compounded, and there's a chart on the next slide that shows you that. Basically, if it says compounded monthly, there are 12 months in a year, so that means N equals 12. Compounded daily, 365 days in the year. Some accountants use 360. I will be using 365 here. And here is the key. This time, right there, that's always in years. If they give you months, let's say they say for 15 months in the problem, you have to use T is 15 over 12, which gives you 1.25 years. T is always in years in this formula. All right, let's go to the next slide where it talks about how to figure out N. Now, you have to figure out N by reading the problem. Nobody tells you N equals 1. It says, you know, you compounded monthly, and you have to realize there are 12 months in a year. So N is always the number of the things they say. They say months, there's 12 months in a year. They say quarters, there's 4 quarters in a year. Semi-annually means twice a year. Daily means there are 365 days in a year, so it happens 365 times in 1 year. Annually is once per year. So that's how you figure out n, by reading the problem. And if so, n is figured out this way and t is always in years. And because n is figured out this way, that is why t is always in years in the formula. Let's take a look at an example. The first thing you have to do is read the problem just to get some idea of what's going on. Find the accumulated value. So that's the a at the end. So a equals p times 1 plus r over n raised to the nt. The other trick here is you have to figure out the nt first. Sometimes you run into an order of operations issue, particularly on scientific calculators. Be in the habit of putting that in parentheses or figuring out nt first and then just using that number in the formula. So the accumulated value of a $3,000 investment for 4 years at 8% if the money is compounded monthly. Wow, 8%, I haven't seen that in a while, but I do remember times when that was true. So let's identify what we have. We want A. That's what we're solving for. P is how much we invest. That's your 3,000. T is in years, and they tell me it's 4 years, so that's good enough to change anything. And R is 8 over 100. That's what percent means. 8 divided by 100, which is 0.08. Be careful, people use 0.8 a lot for that by mistake. So in your calculator, you're going to do 3,000 times 1 plus 0.08 over, wait a minute, what's n? We haven't figured out n yet. N is monthly. N is 12 over 12. Now you want to be careful, and you're going to raise this to an exponent however you do that in your calculator. And on the older TI operating systems and on scientific ones, this gets people in trouble. 12 times 4. If you don't put that in parentheses, the calculator doesn't know the whole thing's an exponent. It just thinks the first part is, just thinks the 12 is. So it would do this to the 12th, then multiply by 4. You don't want to do that. You want to raise that to the 48th. The other way around that is calculate nt as basically one of your variables, and then just use that in this space for the exponent for the formula. That's an order of operations calculation you just have to be really careful with. So I think I did this on the next page. This is what you should get. Try this in your calculator, make sure you're getting it. Now notice I didn't write the parentheses around this. That's dangerous. You have to put parentheses around that and be in the habit of doing that. If you get an answer that's not that, instead of doing not what I show here, 4,127, instead of doing the 12 times 4 for the exponent, do 48, which is 12 times 4, and see if you then get a right answer. If then you get the right answer, the problem is you didn't put parentheses around this exponent. All right, so here's another problem. This time, the problem is the same, except for the fact that I've said it's compounded daily. And what that means is n is now 365. And nt will be 365 times 4 if you want to use that as a single number, putting that into your calculator. So you're going to do 3,000, it's still the p. 1, that 1 is always the same. It's still 8%, so it's 0.08 over 365 this time. Now don't calculate this out separately because that's going to be a tiny number and you're going to round it to 1 and then you're going to get wrong answers. Put all of that in together raised to the 365 times 4. And you can calculate this number ahead of time and just use the number, or you can put it in parentheses like this. And when you do that, you see you get a little bigger number than we got last time. Last time we had 4,127. The more frequently you compound, the bigger the number is. So, what if as soon as the interest hits the account, we compound it again? Well, that's where we have to use this e as the base. And I'm going to go back a few slides to where we looked at e for the first time. And I think I kind of skipped over this. This is where e comes from. It's what we call a limit. As n goes to infinity. So, and you'll see this in calculus, the limit as n goes to infinity, as n gets really, really huge. And we've talked about that in the context of horizontal asymptotes and things getting big. 1 over n will get really, really tiny. So you're adding a really small amount to the one. So you say, well, this is going to get close to not growing at all but the problem is this gets really, really huge. And because this is an exponent, its hugeness swamps out that hugeness. But at some point they're in a tug of war. And when you when you get to really, really big numbers of n, if you start putting in bigger and bigger numbers of n for this, you'll see that you start, first you get to 2.7, it levels off that, then the 2.71 kind of, and then eventually you see that, if you're only looking at 3 digits in your calculator, that's all you ever get. 3 decimal places to the right, rather. So as n gets really, really big, well, n was how many times per year we were compounding. Monthly was 12, daily was 365. But now, what if we compound the moment, going back to the slide we're on, the moment the interest hits the account? Then that's an infinite number of times we're compounding, which is as big as you can get. So that formula we had, where we had 1 plus r over n to the nt, condenses to this, a equals pe to the rt. And again, you're going to multiply the rate times time in the exponent or put it in parentheses. It's a little simpler formula because the n is built in to this e. So if I want to find the accumulated value of that same $3,000 interest, but $3,000 principal. So I get the principal is still $3,000. Yep, sorry, I'm increasing my principal there. The investment time is still, t is still in years, and I kept the same interest rate to keep the comparison easier to make. Now the money's compounded continuously. There is no n. As soon as you see this word continuous, you know you're using this formula instead of the one with the 1 plus r over n in it. As soon as you see continuously, it means you use this formula, and it's the only time you use this formula. So what I have is a equals 3,000. E, now RT is 0.08 times 4. I might do that out ahead of time and just use 0.32, or I must put it in parentheses. Some calculators you don't have to put it in parentheses, but to be safe, all of you should put it in parentheses. Now everybody try that calculation, and what you see is this is the largest number we've seen so far. I mean, it's close to some of the others, just that the pennies are a little bigger. But this is what you should get. Make sure you can do that accurately in your calculator. All right, so there's some things to think about and try. And in the homework, have the formulas in front of you. Knowing which formula to use, the only time you use this one is when you have continuously compounded. You have to read the words carefully. This is not, these calculations are just a formula. They're not as much about the math. The only other thing I could say, too, as way of a hint, is if instead you're told you want A to be some number, let's say you want A to be $10,000, and you've got to find P, what you have there is 10,000 equals P, and let's use the same interest rate we were using here. Compounded monthly, we'll say it was, over 12, and you have 4 years, 12 times 4. To solve for this, basically you calculate this, you get 1,000 divided by 1 plus point, oh, I said 10,000, didn't I? 0.08 over 12 to the 48. You can solve for P this way. You could, if you want to do this in 2 steps, find a number for this by doing all this out, and then divide 10,000 divided by that will give you the principal. That's the other way this could be asked. Instead, if they tell you the amount at the end, figure out all the numbers, and instead you put the amount in the end on the left, and you calculate the principal. All right, email me your questions, and see you next time.